Hello, in this video I would like to discuss about one of the important parameter which will have a huge impact on the simulation accuracy. When we usually do the simulation in our electromagnetic softwares and when we have a comparison between the simulation and measurements, sometimes we feel that there is a large discrepancy between the simulation and measurements. At that time, we will confuse that whether it is mainly because of the simulation result or is it because of the measurement inaccuracies. So these all the simulation softwares are like a huge toolboxes. So it will be processing whatever we are giving it as the input. So when we are giving the accurate inputs, it will provide as the accurate results. So if there is any discrepancy in the input that we are providing, the result that we will be getting will not be accurate. So we have to be careful in each and every input that we are providing. That is, we have to be careful in the modeling, meshing, and the boundary settings. Everything we have to be carefully considered to get the accurate result. So in this video, I would like to discuss one of the important parameter, that is the meshing, which will be having a huge impact on the simulation accuracy. So let's see what you have to be taken care while you are doing the simulation in any electromagnetic softwares. So let's see that.
So let's see what is mean by a mesh. So when you are doing a simulation in an electromagnetic softwares like CST, HFSS or anything, what it is doing is it is actually solving the Maxwell's equations and trying to find out the electric field and magnetic field distribution. So if it has to solve these type of electric field and magnetic field distribution, the one thing it has to do is it has to divide that large problem domain like antenna structures or anything into finite elements so that it will be easy to solve that partial differential equations in each of these tiny elements. So the discretization of the entire structure into these tiny elements is known as the meshing. So meshing is an important parameter that we have to consider when we are considering any simulations. So the discretization of this domain. So if we are considering any solid structures like antennas or anything, we can divide the structures into two types. Like it can be divided into volumes or like any surface discretization. So it will be considering only the surface. So they are of two types, volume solvers and the surface solvers. So if you are going to use any time domain or frequency domain solver, the discretization will be in the uh, 3D space. That is, the entire structures will be discretized into smaller cubes or tetrahedral like structures. If you are going to consider the surface solvers, only the surface of the geometry will be considered. So in that case, we will be considering the method of moments method and it will be using the Green's function. The one of the main important parameter that we usually consider while doing the simulation is the mesh element has to be the fraction of the wavelength at higher frequencies. So this is one of the important parameters that we have to consider. That is, if we are going to discretize this structure, the each element size has to be fraction of the wavelength. That means that if we are going to use the higher frequency, we know that the wavelength will be very less, right? So in that case, the number of mesh elements will be very high. So if you are going to do the simulation at high frequencies, as the mesh size will be high, it may be taking a lot of time. So let's see how these are happening. So next we can see how these are coming into effect for different types of solvers. So when you consider the CST simulation, we know that it has lots of solvers like frequency domain solver, time domain solver, integral equation solvers, etc. Right? So these solvers will be solving different problems like antenna radiation pattern, RCS of the structures, etc. So they will be using different computational techniques to solve these problems. So these computational techniques can be like finite element method, finite difference time domain method, or method of moments, etc. So these computational techniques will vary depends upon the problem that we are using. So based on the solvers, they will be using different meshing techniques to solve the structure that we are using. So let's see what are they. So if you are going to use a frequency domain solver, it will be using a tetrahedral meshing. It will be a volumetric meshing, and it is mainly used for the broadband frequency solutions. So this is structure of a tetrahedral geometry. So all the structures will be divided into these type of structures. In case of the time domain, the structure will be divided into hexahedral structures. So hexahedral means it will be like a cuboid structure which will be having the six faces. So the structure will be divided into these type of structures, meshes, and the solutions will be based on these type of meshing. So it is mainly for the time domain solver. In case of the surface meshing, it is mainly used for integral equation solver, that is used for the RCS of the structures. So in that case, the structure will be very huge. So we can use the integral equation solver, so which requires only the meshing on the surface level. So these type of volumetric meshing will not be required. So the number of meshes will be very less. So this is the basic idea of the meshing. So we have seen that if our solution domain is like time domain solver, it will be providing the meshing in hexahedral, right? So let's see how you can check that. So I'm just going for the waveguide and I'm going to take the time domain. So we have seen that if it is a time domain, the meshing will be hexahedral. So let's see that. I'm not going to set any frequencies. I just finish. Okay, and to check the mesh, I'm just going to create a structure, not much, just something, so that I can view the mesh. So if you go to the global properties, here you can see that the mesh type is hexahedral. That is, if it is the time domain solver, here you can see that it is a time domain. The solver is hexahedral mesh. So I have opened two simulation files from the examples. So if you go here, like a component library, you can check different structures. So here I have taken these two files, magic t in frequency domain and magic t in time domain. So just to give an idea about how the meshing will be seen for the time domain and frequency domain. So this is the time domain. So in case of the time domain, we know that it is a hexahedral. Hexahedral means it is a cube structure. So if you go here, means if you want to see, okay, sorry, if you want to see the mesh, you can go here and click on mesh view. So this domain will be seen. So if you want to see the mesh, you can see that on a cutting plane. So if you see here, you can see this is a part of the cube. You are not able to see the cube as the 3D as it is seen on a cutting plane. So if you increase the structure, you can see how the cuboid structure will be varying based on the structures. So this is how the hexahedral meshing will be done. So next, let's see how it is going for the frequency domain. So in case of the frequency domain, the meshing will be tetrahedral. So if you go here and check here, you can see that it is tetrahedral. So if you want to check the mesh view, you can click on the mesh view and it will be showing like this. So if you want to see how the tetrahedron is looking, you can just click on the cutting plane. So here you can see that the tetrahedral meshing. So he can see that how the different tetrahedral structures. So if you consider here, you can see that one, two, three tetrahedron structures are actually fitting the geometry here. So likewise, the tetrahedral mesh cells are completely covering the structures. So here you can see that how the meshing is done beautifully. So based on different cutting plane, you can check how the meshing is done. So here you can see that by using this tetrahedral or hexahedral, it is very easy to mesh the structure. So the meshing actually depends upon which solver you are using, and this is an example of a surface meshing. So here you can see that it is an integral solver, and I have taken the mesh view. Here you can see that how the meshing is happened on the surface waves, sorry, surfaces. So here you can see how the surface meshing is done. So in integral equation solver, we are using the method of moments. That's why it require only the surface meshing. So I hope you get some idea about what is the meshing and how it is um, specified. So let's see some of the parameters. So I'm just going for the magic frequency domain solver. So if you want to go for the global properties, this is the global mesh settings. So if you set some parameters here, based on this the meshing will be happening. So this is one of the parameter. If you improve means increase this value, you can see how the meshing is increased inside the structure. So this parameter you can use to increase the meshing, and here you can check how many number of total tetrahedrons are used to cover this structure. Here you can see that if I am going to use cell per maximum H as 14, you can get around 3198 tetrahedrons to cover the structure. So let's increase maybe to 30. This is just to show how the meshing is improving the structure. So here you can see that now the tetrahedrons are red, means number of tetrahedrons are increased. Here you can see that it is around 33,000, because for a certain cell we are going to use 30 number of meshes. So maybe I will explain this quick. Let's see that. So let's see how the meshing is improved based on this lambda by 10 or lambda by 20 settings. So here I'm going to consider a frequency of 2 gigahertz where the wavelength is around 15 centimeter, and here I have considered a structure having the length as 15 centimeters. So here I'm going to consider only in one dimension, not in the entire dimension like height or anything, but only on these geometry. So these two boxes are of 15 centimeter. Here we will be going to see how the meshing will be having an impact. So if we say mesh is equal to lambda by 10, that means that here lambda is 15. So the entire structure where the lambda comes. So here the structure dimension is equal to lambda, right? So this structure has to divided into 10 uh, same structures like this. So this is how the meshing is happen. So if it is like lambda by 20, it has to be divided into 20 structures, like means the entire domain has to be divided into 20 structures. So here you can see that if the meshing like lambda by 20 is used, the structure will be discretized into very smaller elements. So in this case, we can see that the number of mesh elements will be increased. So that is what that settings actually means. And one of the also important thing is this meshing will also have impact on the frequency. Like if we are going to say the frequency is 20 gigahertz, then the wavelength is 15 centimeters. So if you are going to consider a 50 centimeter and the meshing is like lambda by 10, so we have to divide this structure into 10 um, discretized elements. So if we are going to use that the same geometry on a 15 centimeter structure, but here the frequency of our simulation is 30 gigahertz, that means that our lambda is 1 centimeter. That means that if we have a dimension here like 1 centimeter, this 1 centimeter has to be divided into 10 elements. So each and every 1 centimeter has to be divided into 10 elements. That means that if we are going to use the same mesh settings for different frequencies, we can see that with increase in frequency, like if the frequency is 30 gigahertz, the wavelength is more and the number of mesh will be more. So this is one of the important thing that we have to be considered while doing the. So now we have seen that how these meshing will have an impact. So here you can set the minimum cells based on the automatic or based on the cell per wavelength. So this cell per wavelength is what we have seen earlier, lambda by 10. If it is like automatic, it is based on the actual values. So this is how the mesh setting is. So this same will apply for the time domain also. So let's see that if you go for the global properties, if you are maybe global properties, and if you are going to, so now you can see that with cells per wavelength, that is the 20 mesh settings, the number of cells is around 18,000. If you reduce that, maybe we can see the mesh view. So, okay, so now I'm going to reduce the mesh. So here you can see how it is getting, the number of mesh cells is getting impacted. Here you can see that the number of mesh cells is getting reduced. So this is how we are defining the mesh cells. So this setting has huge impact on solving the electromagnetic equations. So it is very much advisable to use very accurate mesh settings to get the accurate results. And maybe if you go to the specials, you can see that the material based refinement. So this material based refinement is used when we are using different types of materials like PECs and different types of dielectric. So this meshing will be based on these materials. Here, as I have only one material, this will not have much impact, but if your structures has different types of dielectric materials, it is desirable to use the material based refinement. And we also have snapping, so I may show what is the importance of snapping here, and discretizer. So this setting, perfect boundary approximation, is desirable when you have the structures like dielectric and metal. So this will improve the accuracy of the simulation. So this is regarding the global properties of the meshing, and in meshing we also have the local properties. So let's consider this case. So now we know that this is how the meshing is done. You can see how the meshing is done here, right? So if we are not able to use this much meshing for the entire domain, because based on the number of meshing, the simulation time will increase and we should have the proper CPUs and GPUs to solve this. So let's reduce this thing. And if I have to increase the meshing on a particular structure, let's say if I have to increase the meshing here so that my simulation accuracy will be improved, so we have another setting known as the local meshing. So I'm going to select that solid. So here you can see that this solid one correspond to this structure. So my intention is to I have to improve the meshing on this structure. So if you right click here and go to local mesh properties, here you can see that there is a different mesh setting. So here you can use this mesh setting to improve the accuracy of the simulation also. So you can set one thing on the global meshing and use different for the global mesh. So if you have any antenna structures and if you have to improve the meshing on the PEC structures, you can use this. So here I am going to use maybe minimum mesh set width setting. So this width setting we have to provide. So I'm going to use maximum step width as maybe 3. So I'm going to use as 3. So let's see how it is improving the machine. Okay, so okay, it is not updated. Okay. So here you can see that meshing on this geometry and this geometry is different as we have provided more meshing here. You can see the meshing on this structure is now dense. So this meshing we can use to improve the accuracy of the result. So this is one of the local mesh setting that you can consider while doing the frequency domain simulation. And in case of the time domain simulation, we can also have the local meshing. So if you right click, you can go to the local meshing and do different settings. Okay, so in this group, you can see different mesh groups. So based on the different mesh settings, so you can provide different mesh settings for each domain. So maybe I will set this as mesh group 1, and maybe I will set it as mesh group 1, and I will set different mesh group having different mesh settings for another solid. So you will be having different mesh groups based on the local mesh properties. You will be having different mesh groups, and if you want to change the mesh group to mesh group 1, you can just drag and drop it here. So that mesh settings will be same as the mesh settings of the component 1. So likewise, you can change the mesh settings of individual structures. And one more thing, I would like to show you how the snapping works. Maybe I will just open new, just a new structure, just to show how the snapping works. Okay, so I just want to show you the snapping. So I'm going to use, okay, minus. Okay. So I am going to create a multi-layer structures to show the impact of snapping. Okay, copy, translate, is it? I'm going to use different material. Okay. So we have a multi-layer structure now. So I just want to show you how the snapping works. Okay, I'm going to use some frequencies from 1 to 10. So here you can see that how the meshing is here. So let's go to global properties and special. So here you can see that these are getting enabled, snapping. So let's enable disable that and let's see how it is now. Okay, so you have seen some change in the meshing. So here you can see that if you consider this mesh is considering containing both the material like PC and FR4. So uh, this mesh is containing different structures. So while solving the EM equations, this will be causing some issues. So to avoid that, we can use snapping. Snapping means the mesh will be snapped based on the different materials. So if you go to specials and if you enable these snapping, you can see that the mesh is now snapped based on the material properties. This is one of others important meshing that you have to consider while doing the simulations. And one of other thing is to show you how the meshing will be changed based on the frequencies. So now you can see that we have chosen the frequencies from 1 to 10 gigahertz and you have this much number of cells. So let's change the frequency to maybe 10 to 30. So here you can see that now the number of meshes are increased inside the structures. So even without changing any of the global properties, you can see that the number of cells are increased based on the frequencies. So while doing the high frequency simulations, it may require good GPUs and CPUs for our simulation. So it is very important to consider the meshing while doing the simulation. So I think if you go to the help, you will get a lot of details about how the meshings in time domain and frequency domain works. So it is very better to have a complete picture about these mesh settings and how these mesh settings will be having an impact. So here also you can see that if the mesh on these type of tiny structures is very dense, then it will cause the problem. So it is better to have meshing like this. So if you go to maybe different mesh properties, you can see how these mesh settings will be having an impact. If you go to the snapping, you will get a lot of details from this help. So it is better to have a complete picture about the meshing. I hope you get some ideas. Thank you.